Section 5.2, Definite Integrals. So we're continuing the idea of Riemann sums. And the whole purpose, and generally the whole idea of this section, is to see and introduce the idea of Riemann sums and build it to an integration. So our goal, is to go from Riemann sums to integration, which is really cool because we kind of know how to kind of build this integration since we did it in section 4.9 and we talked about antiderivatives. And that's a key process to being able to integrate. Okay, so let's read from our text. We introduce Riemann sums in section 5.1 as a way to approximate the area of a region bounded by a curve y equals f of x and the x-axis on an interval from a to b. In that discussion, we assumed f to be non-negative on the interval. Our next task is to discover the geometric meaning of a Riemann sum when f is negative on some or all of a and b. So what do you think happens? Let's take a look at an example. Evaluate and interpret the following Riemann sums for f of x equals 1 minus x squared on the interval from a to b with n equally spaced subintervals. We're going to do part A. Using the midpoint Riemann sum from a to b being from 1 to 3 with n subintervals. Okay, so we have to find our delta x. We take our highest minus our low divided by number of subintervals. We get 0.05. So starting at 1 and ending at 3, we start at 1 and then to our next one, we add 0.5. From 1.5 to our next, we add 0.5. And that's how we get all of our intervals. But because we want the midpoint, we have to find the midpoint between those 2 points. So we have 1.25, 1.75, 2.25, and 2.75. We're going to plug in those values, our midpoints, into our function, which is 1 minus x squared. So we're going to multiply our delta x, that 0.5, into our number that we're going to evaluate by. And you can just factor the 0.5 out and evaluate and add them up. Now, those sums are actually negative. So our answer is negative 6.625. Notice we get a negative area. Why do you think that's so? So in a general sense, if we're working on some figure that is above our x-axis, we're always going to result in a positive area. If we work with an area that is below our x-axis, we're going to result in a negative area. Our definition for that is net area. Consider the region R bounded by the graph of a continuous function f and the x-axis between a and b. The net area of R is the sum of the areas of the parts of R that lie on the x-axis minus the sum of the areas of R that lie below the x-axis. The definite integral. Riemann sums from a to b give approximations to a net area of a region bounded by a graph of f and the x-axis between a and b. We see that the Riemann sums approximate to approach the exact value of the net area as a number of subintervals n approach infinity. The length of subintervals also approaches infinity. So what we're saying here is, let's say we're trying to find the area of this function f of x. We can create as many subintervals as you like. You can make a small amount of 6 subintervals. You can make it really small and make more subintervals, say 40 of them. And it doesn't matter because at the end of the day, they're all reaching the same number as if you were to have an infinite amount of subintervals, to where there's almost no distance between them. Next definition is the general Riemann sums. Suppose the closed interval x0, 1 x1, comma 2, all the way to xn minus 1 to xn are subintervals from a to b, with a equaling x0, which is less than x1, which is less than x2. So all we're saying is, don't let this notation fool you. Just say we have our first interval, and we're going to do as many intervals as we're being asked to or want until we reach some point. Let delta xk be the length of subinterval from xk minus 1 to xk. Let xk star be any point in xk minus 1 to xk for k equaling 1, comma 2, all the way to n. So we can, in a sense, create any point on our closed interval. And we see here a little picture showing us that this little point kind of varies anywhere between the intervals. So you see here it's more to the right, here it's more to the left. So that's our general Riemann sum. This is our important definition for the section. The definite integral. The function f defined by the closed interval from a to b is integrable on the closed interval from a to b if the limit as delta x is approaching 0 of the sum from k1 all the way to n of f of xk star delta xk exists and is unique over all the partitions of the closed interval from a to b and all choices of xk star on the partition. This limit is the definite integral of f from a to b, which you write the integral from b to a of f of x comma dx. I'm sorry, f of x dx. That is our punchline. We took 2 sections to develop this idea. And honestly, you can stop here. We're going to go ahead and work more in the next sections to see how we go about it and how it all works. But let's continue and finish this section. Theorem 5.2, integrable functions. If f is continuous from a to b or bounded from a to b with a finite number of discontinuities, then f is integrable on a to b. Now, we're going to talk more about the process of finding the area under the curve in detail in the next section. For now, we're just going to be clever and work with areas of figures that we already know. For this example, use familiar area formulas to evaluate the following definite integrals. So I have example A and B done for us. And I made this so our video wouldn't be too long. Our first problem, A, is the integral from 4 to 2 of 2x plus 3 dx. All right, so we plot our line, y equals 2x plus 3, and we see where the point at 2 and at 4 where they are. We enclose the area and we want to find the area underneath that curve. In this case, it's not really a curve, it's just a line. We see we have a rhombus. I'm sorry, a trapezoid. And the area of a trapezoid is 1/2 times the height plus a times of a plus b. So we have a height in our picture of 11. And our base of our rhombus is 2. And we see we also have this other height of 7. So our area would be 1/2 times 2 times 11 plus 7. We get 18. And in a way, we are answering our integral because we did find the area under the figure, under the curve. Next, we have b. The integral from 6 to 1 of 2x minus 6 dx. So I graphed your function for you. We have 2x minus 6. And we have our line. And if we enclose it from 1 all the way to 6, we see that we have an area below the x-axis and an area above the x-axis. Notice that below the x-axis, this is going to be a negative area, and this is going to be positive. Let's find these areas of these triangles. We see we get a triangle. Remember that the area of a triangle is 1/2 times base times height. The first triangle, our little triangle, has a height of 4 and a base of 2. So we have 2 times 4 times 1/2, we get 4. Remember to change that to a -4 because it's below the x-axis. All right, next we have our second triangle with a base of 3 and a height of 6. So 1/2 times 3 times 6, we get 9. So our integral is made up of 9 minus 4, which is 5. I'm out of space, but C would have been a semicircle. Reversing limits and identical limits of integration. Suppose f is integrable from a to b. 1. If the integral from a to b of f of x dx, if we switch the bounds, notice instead of going from a to b, if we go from b to a, it's going to cause a negative to be in the front. And if we integrate over the same point, a to a, our answer is going to be 0. Five point four, we have some properties of definite integrals. Our definition from above. We can also add them up and split the integral amongst terms. We can factor a constant out of the integral. And we can split the bounds accordingly. And lastly, we have to be careful with absolute values because we have to consider if the bound or what is below the x-axis. So here we have an example. I'll go through A and B, but I have the other answers there too. So this is just being clever and working with some values of integrals. So assume that the integral from 5 to 0 of f of x dx equals 3, and the integral from 7 to 0 of f of x dx equals -10. Evaluate the following integrals if possible. So A is saying the integral from 7 to 0 of 2 f of x dx. So we see this constant, and according to property 4, we can go ahead and move that constant out so that we can work the integral without working with that constant. From above, we see that the integral from 7 to 0 of f of x gives us -10. So we get that -10, we multiply by that 2, we get -20. All right, B, our integral from 7 to 5 of f of x dx. Okay, well, I don't have from 7 to 5, but I have from 5 to 0 and 7 to 0. And if we have 7 minus 5, that gives that same difference of 2. So we can take the integral from 7 to 0 and from 5 to 0 to get our answer. All right, I don't want to make this video too long. The whole idea is we're moving away from Riemann sums and developing this as an area under the curve, and we're going to use integrals to do so. And that will lead us to our next section. Thanks.